Okay, so today I'm going to talk about hierarchical clustering and then fuzzy clustering in the second lecture, and then I'm going to present the second assignment. So today we're going to finish all the subject matter that you'll need for the second assignment. Okay? So I'm going to start with the idea of hierarchical clustering, and then to give you examples of agglomerative clustering and divisive clustering, and also an application of agglomerative clustering to clustering features instead of clustering examples. So let's start with this idea of hierarchical clustering. We saw last week algorithms for partitional clustering based on centroids, based on density and so forth. And the idea was to join together into the same group those examples that were similar and separate into different groups examples that were different. But all those clusters that we created were on the same level, so to speak. So we were partitioning our data set into a set of non-overlapping clusters. With the hierarchical clustering, we want to create clusters of clusters. So you can imagine a tree as an example of a hierarchical clustering, where we have branches that include sub-branches and sub-sub-branches and so forth. So we have this notion that there are clusters inside that are part of larger clusters at the higher level of the hierarchy, and then higher level and so on. So we can talk about species, genera, and then families, kingdoms, and so forth. We can do this with organisms. We can do this, for example, with gene activity patterns, because the similarities in the expression of some genes may indicate that those cells have the same, belong to the same tissue or the same strain of marker organism and so on. And we can create these dendrograms, these tree-like representations of small clusters that are parts of larger clusters, and then we go up the hierarchy. So that's where the name comes from, hierarchical clustering, because we are building a set of levels from top to bottom or bottom to top, depending on how we cluster them. So this is a good way of clustering examples when there is some underlying structure with this hierarchical nature that we want to capture. We can represent hierarchical clusters as a dendrogram. So dendrogram is a general term for these tree-like representations, where we can, for example, in this case, suppose that we group together these two examples, D and E, and B and C, because they are very close together, and so we have these two clusters here. And then F seems to belong to this cluster, so we create an additional level where we have this DEF cluster that includes the DE cluster and the F element. And then we can group all these together, B, C, D, E, F, and then finally A joins on the top level. So we can create clusters at different levels and build that hierarchical structure organizing the data. So one thing we need for clustering always is to have some notion of examples of similarity or difference between examples. So we can get a general term like proximity, which is not necessarily a distance, but something that indicates whether or not two examples are alike. Similarity, dissimilarity. Distance is a specific case of dissimilarity because a distance needs to have these properties. It has to be 0 or positive. It's 0 if you have the exact same point, otherwise it's positive. It's symmetrical, and it fulfills that triangular inequality. So if you have a measure of dissimilarity that respects those three conditions, then you have a distance measure. But you can do clustering without having a distance measure by having some measure of similarity. So this is for the examples, and we can use many different measures to try to quantify how much the examples are alike or are dissimilar. We can use measures of distance, for example, Euclidean distance. We can use squared Euclidean distance. This is Manhattan, so in this case, Manhattan would be norm 1 distance. This Euclidean is norm 2. We use the square there. But then we can, for example, normalize by the variance of the data. So we are measuring distance in units that are relative to how spread out our points are. In this case, Mahalanobis distance. Hamming distance can be used to measure distance between strings or between sets of categorical features. So basically, we are measuring the number of differences between these sets of features or the strings, and so on. There are many different ways of trying to measure similarity between examples. So this is one thing that we need both for hierarchical and partitional clustering, because clustering is about putting together examples that are similar and separating those that are dissimilar. So we need some measure of similarity or dissimilarity. But in addition, when we do hierarchical clustering, we also need to consider whether or not two clusters belong together or should be broken apart. So we are not only considering similarity between different examples, we also need to consider similarity between groups of examples. And this is the idea of linkage, how we can compare whether or not two groups of examples should be together in a higher level cluster, or if they should remain apart, or if we are going from top to bottom, how we should split apart a group into subgroups. So with hierarchical clustering, we not only need similarity measures between examples, but also a way of measuring similarity between groups, and that is the notion of linkage. We have several examples I'm going to give: single linkage, complete linkage, and so on. So this is an example of a linkage measure, which is single linkage, in which the distance, we measure the distance between two clusters as being the smallest distance between the examples in the clusters. So with single linkage, the distance between this cluster and that cluster is the distance between the nearest examples in the two clusters. Complete linkage is the maximum distance. So note here that even though we are using the same dissimilarity measure for the examples, it's distance in both cases, the way we group groups together, so clusters into higher level clusters, can be different depending on how we compute the linkage, on how we compute the similarity between clusters. So single linkage, we use the smallest value of the distance. Complete linkage, we use the largest. Centroid linkage, we use the distance between the centers, the mean points of each cluster. And then we have average linkage, we use the average of all the distance between the pairs of points from one cluster to the other, or the median, or we try to choose clusters in order to minimize the sum of squared errors. So basically the squared distance to the center of each cluster, or the distances between the examples in the clusters. And so we have different linkage measurements, so different measures of how similar or dissimilar the clusters are, or how adequate or inadequate it would be to bring them together or to split them apart. Okay. So difference between the similarity measures and linkage is that linkage is something we apply to the clusters, to the groups themselves, in order to compare how different they are. So with hierarchical clustering, we need some way of comparing, of measuring the similarity or dissimilarity between examples and also between clusters, because then we need to group clusters with one another or to split clusters apart. The advantages of hierarchical clustering is that depending on the kind of algorithm that you use, but you can think that during the training part where you are creating the clusters, you don't need to specify a number of clusters. You can just draw the whole tree, and then you have this idea of the structure of what goes inside each group, which groups belong to each higher level group, and so forth. And this hierarchical organization may correspond to some underlying aspect of the data that you want to understand. So if the data has this hierarchical structure, it's good to use hierarchical clustering. One example of this is in phylogenetics, or in trying to understand the relationships between living organisms. We know that the closer relatives descend from more recent common ancestors, and then more distant relatives have more distant common ancestors. So we can build this tree of life, which is a hierarchical cluster. Okay, so the question is, if we have new examples, how we can classify or group the examples in the existing clusters. Some clustering algorithms can make it easy to do that. For example, k-means or something like that. It's easy to find which cluster a new example would belong to. Others, for example, affinity propagation, it would be very hard because it depends on all the votes going from examples to other examples. But the main idea here is that when you're doing supervised learning or classification, the goal is to extrapolate from a set of known data points to new data points that you get in the future. So you will apply the classifier to future information, to future examples, and you need to estimate the true error and so on. With unsupervised learning, that is usually not the goal. Because if you already have an idea of which categories you have, then you label everything, build a classifier, and you are in supervised learning. With unsupervised learning, what we want is something that helps us understand the structure in the data that we have. So usually that is not a problem. When you create, for example, a phylogenetic tree, the idea is not to have something that will predict the next fossil that you find or the next microorganism. It's just to organize the ones that you know. So in general, these algorithms are not conceived thinking about what will happen when we find a new point, because that's not the goal. Okay. So in this case, it would not be simple to just assign. In some cases, it could be if you have centroids or something like that, but in other cases, you would have to redo everything if you have new data. So disadvantages of hierarchical clustering is that usually we do it in a single pass, either top-down or bottom-up. So if there are errors during this process, they will not be corrected. They will be propagated to other iterations. So if your clustering algorithm at each level does some mistake, does something that does not really conform to the structure of the data, then it will be frozen in the rest of the hierarchy. And also, it may be confusing if there is no underlying hierarchical structure to your data. So if you apply hierarchical clustering to something that has no hierarchy, then the result will probably be a bit strange. So for example, if you try to do a phylogenetic tree of mammals, the relationship between the species will make sense. But if you try to do that with motorized vehicles, for example, with boats and planes and cars and so on, then the tree will not make sense because there is no hierarchical relation between them. They do not descend from common ancestors or something like that, and they have all the features combined in different combinations that do not correspond to any tree-like structure. So if you apply hierarchical clustering to the wrong type of problems, probably you get something that will be misleading. So let's see how we can do clustering. There are basically two approaches. We can start with all the examples and group them together. This will be agglomerative clustering, bottom-up. Agglomerative clustering will be an example. We start with clusters of one example each, and then we join the best two. We have this linkage measure that tells us which groups are closer, and we start joining the closest groups, and we keep joining that until we have the whole tree, the whole hierarchy complete. Or we can do it the other way around. We can do divisive clustering, top-down. We can start with all the examples in one group, and then we split, and we split again, and we keep splitting until we have the desired number of clustering. So there is a difference in complexity. In general, these bottom-up algorithms tend to be on the order of the cube of the number of examples you have, for example, agglomerative clustering. This can be a bit improved if we use linkage constraints. We'll talk a bit more about that later. But it can take quite a bit of time if you have a large data set. Divisive clustering, in theory, could be worse, could be exponential in the number of examples, because if you have a set of n examples, there are 2 raised to the n possible combinations for splitting into 2 subsets. So if you had to check all of them, then this could take a long time. However, you can use clustering algorithms that are much faster than this to do the division, so you can speed up the process. But basically, what often determines whether you want top-down or bottom-up is what you want the result to be. If you want to start with the root of the tree and then go down some levels until you're satisfied with the number of clusters, then it's better usually to do top-down and divide the clusters. If you, on the other hand, just want to start grouping them together until you have quite a large number of clusters, or only do a few steps like that, and you don't care about the rest of the tree, then it may be easier to do bottom-up, because you only have to do a few steps and don't need to build the whole tree. Okay. So let's see how agglomerative clustering works. We start with a data set, and each example is its own cluster. And then we will join together the ones that are closer, and eventually, since we are using a linkage measure that compares groups of examples, we will eventually find groups that are close to one another, so we'll join them into larger groups and so on. If we keep track of all these mergings of different clusters, we can build the tree from all these links between the groups, and we can compute this. So these were the examples we started to bring together, but then we started to join other examples and join groups of examples, and we have the whole tree of representing this process, and this will be our hierarchical clustering represented as a dendrogram. We may turn this into a partitional cluster. So this is one advantage of hierarchical clustering, if it's appropriate for your data set. After you have the complete hierarchy of clusters, you can select a level in which to partition and convert this into a partitional clustering. For example, we may select this branch here, the first branch, and we split our data into 2 clusters. So we can just cut here. This was the last branch we created when we did the agglomerative clustering. So if we cut this here, we have 2 different clusters. If we go down one more level, we can cut this into 3 different clusters, and so on, 4, 5, whatever we want. So once we have the complete hierarchy of clusters, we can decide how many clusters we want, and we will always be following the same structure of our data. So this is one way of answering the first question I asked in the beginning about this data set, whether we had 2, 3, 4, or 5 clusters. So if you do hierarchical clustering, you have them all there, and you can just pick which is the most appropriate representation in each case. Another thing that we can do with agglomerative clustering is to use constraints. This is generally used with agglomerative clustering because otherwise it tends to be very slow with large data sets. But usually these connectivity constraints are useful to include in clustering, in our distance measures, some additional information about the structure of the data. For example, imagine that the data is distributed this way. So this would be the manifold where the data is distributed. We'll return to this notion of manifold in the second hour, but this is basically a space that is locally Euclidean, but you can have with a surface with a lower dimension, than the one in which the data is represented. So if you can imagine this ribbon here, locally you can use Euclidean distance between the points in the neighbors. Of course, if you follow this ribbon, then the distance along this ribbon to a point here would be much larger than the distance actually in space. But we could impose that as a constraint on our agglomerative clustering to prevent these points from belonging to the same cluster as these ones, because all of these blue points were placed in the same cluster, and this does not make much sense with this structure of the data. So we can do that easily in scikit-learn. All we need is a matrix which has the n being the number of examples we have. We have an n by n matrix of zeros with a 1 if the points are connected. And when we do linkage and similarity, so when we are linking points together into groups and groups into larger groups, the agglomerative clustering algorithm will only consider distances between points that are connected. So if we create a linkage matrix that reflects this, the shape of this ribbon, and we can do this with this neighbors graph. So basically, if we use this function and set, for example, neighbors to 10, then each example will only be linked to the 10 nearest neighbors. And so we create a web of linking, of connectivities between the examples that will always follow this ribbon, because the 10 nearest neighbors to any point are always on the same part of the ribbon. So if we create this web of connectivities here, the agglomerative clustering algorithm will only consider those points that are connected, those connections. And so the result, instead of being this one that we had when we considered the Euclidean distance over all the possible pairs of points, will now be this one, where clusters are in their own parts of the ribbons and do not jump from one part of the ribbon to the other. To do that, we can use, in scikit-learn, we can use this k-neighbors graph to create the matrix of connectivity between each point and the nearest neighbors, in this case the 10 nearest neighbors. And then when we do agglomerative clustering, we impose this connectivity constraint. So only those that are connected count for linking the cluster. Okay? So this is one application of agglomerative clustering, where we include additional information about the structure of the data. You have these parameters for agglomerative clustering: the number of clusters, the affinity used, so what you're going to use to measure the affinity between the points, and then also the linkage, which is what you're going to use for the similarity between the groups. In this case, word linkage is one of the options if you use Euclidean distance, because word linkage joins the groups together in order to minimize the sum of squared error of quadratic distances inside the group. So if you use Euclidean distance, you can use word. If you use different measures, then you can no longer use word, but you can use other, like complete, average, and so on, for the linkage. So this is that measure that decides how the groups will be grouped together, and this will influence how the final result is. So complete linkages, remember, you take the maximum distance between the groups, so it's looking at all the points in the group, so to speak, and take the distance between them as the maximum, so spanning everything. And this will tend to favor larger clusters. So larger clusters will tend to spread out more. If you do average linkage, you get some better results. Usually word linkage is best, because then the clusters are brought together, those that preferentially that minimize the sum of squared distances. So you tend to get better clusters like this, with better frontiers and shapes. But you can only use word linkage if you use Euclidean distance measure. If you don't use Euclidean distance measure, you cannot use word linkage with agglomerative clustering in scikit-learn. So depending on the kind of linkage that you use, you can control that. You can also impose those connectivity constraints if you have additional structure to the data. Well, in scikit-learning, you cannot. In theory, there would be, in theory, you should be able to combine word distances with other measures, word linkage with other measures of affinity. However, since word linkage requires you to measure distances, the way it's implemented is that it uses the distances that are already measured. So there is no theoretical impediment or something that would forbid using word linkage with different affinities, but in this case, in this implementation, it has to be like that. So another way of doing hierarchical clustering is to start from one single cluster. Everything is in the same cluster, and now we divide. So one example of a divisive clustering algorithm is bisecting k-means. This is, even though divisive clustering in theory could be very slow because you have an exponential number of combinations of splits to do for each group, bisecting k-means is very fast because k-means with a k equal to 2 is very fast to compute. So what we do is we start with a single cluster for all examples. Then we repeat selecting one cluster. This, by the way, is a simplified version of the bisecting k-means algorithm. Then we select one cluster, we split the cluster with k-means, with k equal 2, and then we repeat this. In fact, the original implementation, since this is very fast, repeated this split several times for the same cluster, and then chose the one with the best split. Because k-means, you start with the centroids at random, and then it converges somewhere, and it does not always give the same results. So since this is fast, you can do that a certain number of times and pick the best split between the clusters, for example, measuring the distance to the centroids or something like that. But the general idea is that we start with an example, with a single cluster, we split into two, and then we keep repeating that. So everything is the same. We keep computing the k-means clusters with k equals to 2. So for each cluster, we split into 2. And then we select the next cluster to split and keep doing that. The selection for the next cluster can be more sophisticated because you can consider how spread out the points are, for example, using the quadratic sum of distances. But in this case, I'm just splitting on the cluster with the largest number of points. So at each iteration, I pick the one with the largest number of examples and split that one. Then I pick another with the largest number of examples and split that one, so on. So this way we get also hierarchical clustering because we can remember when we split each pair of clusters, and we can produce the tree with all the splits all the way until the end. So basically, for divisive clustering, if we were to do an exhaustive search, so if we were to consider all possible ways of splitting each cluster, this would be exponential on the number of clusters, but we can use an algorithm that does this faster, for example, k-means, and then we do the divisions with much less computation than that exponential on the order of the number of examples. So if you have a fast algorithm for splitting and it works well in your case, or alternative, if you just want to have the first few splits, so if you want to have a few large clusters and not do the tree all the way to the end, then divisive clustering can be much better than agglomerative clustering. So basically, if you want many small clusters, it can be more efficient to use agglomerative clustering because you start with everything spread out and then you just need to join a few times. If you want a few large clusters, then it's maybe best to start from the top and do divisive clustering. Another thing that we can do, we've been seeing so far, clustering applied to the examples, but we can apply clustering to the features. The idea here is that when we are doing clustering, we usually, like we did with scikit-learn also in supervised learning, we have a matrix where each feature is a column and each example is a row. So if you can imagine that you feed that into a clustering algorithm, it will cluster the rows according to some similarity measure, because those are the examples. But suppose that you just transpose the matrix and you put the features on the rows and the examples on the columns. If you feed that into the same algorithm, now it will cluster the features according to how similar the values are in different examples. So it's now looking at the features as examples and clustering them by their similarity. In fact, we don't need to do this in scikit-learn because there is a specific class for agglomerative clustering that does this, but this is the basic idea. We can just consider, instead of considering examples having features, we consider the features to be the examples and the value of the feature in each example to be the features that describe that particular one. So we are going to cluster together those features that have the similar values over different examples. So if the features have the same value on many different examples and another feature has the same values there, then those features will be similar. It will be a similar vector. So to illustrate this, we're going to use the beneath data set. This is a basic data set very used in machine learning. So this is the modified handwritten digits data set, where the digits written by hand were digitized, were all resized to be in this 8 by 8 square image, so in this case, and centered on the image. So these were handwritten digits represented there in 8 by 8 pixels. We have 64 features for each of these digits. So now we have the 1,797 examples, each one with 64 features. We're going to transpose that matrix, and this will be as if we had 64 examples with 1,700 and something features each. Now we're going to cluster these 16 into 16 vectors, these 64 vectors into 16 clusters. And also we're going to restrict linkage. So we're going to add a connectivity constraint so that only adjacent pixels are counted when bringing the clusters together. So if, in fact, we are clustering the different pixels in the image according to how their brightness changes over all the examples. So two pixels that have similar variation of brightness over all the examples will be clustered together. But we don't want to cluster, for example, a pixel here and a pixel here, because that wouldn't make much sense. So we're going to add this connectivity constraint that only pixels that are next to each other in the image can be put in the same cluster. So this is the original data. Now this is the implementation. We can load these digits. So we have this data set in scikit-learn that already has this example data sets. We can load the digits here. We get the images and we reshape everything so that we have one image per row and as many columns as necessary. So in this case, 64 columns. Now, we could do the transpose to do clustering. We're not going to do that because we already have this feature agglomeration class that does this implicitly. So it's agglomerative clustering applied to the features. And we're going to create this connectivity here by using this grid to graph function, which basically takes a grid of n by n and then returns a matrix of n squared by n squared with a 1 for all the cells on the grid that are connected. So if we give this function the shape of the image, we get the connectivity between adjacent pixels. And this is what we're going to use for the connectivity constraint on the clustering algorithm. Then we fit, we compute the clusters with fit, and then we have the transform. So this would be the initial data with 64 features, we transform it to 16 features by clustering the features. But then we can also do this inverse transform, which is taking the reduced features and projecting them back into the original 64 features by copying the ones that are in the same cluster. So all those that are in the same cluster will get the same value. So this is the result. This is what the clustering algorithm did. So taking all these examples, it concluded that these pixels seem to be very similar. So these are all in one cluster. These pixels here are another cluster, these two another cluster, these two another cluster, and so on. So this is based on how similar are the vectors of these features when we consider them in all the examples. And this part is easy to understand because this is mostly black for all examples. So all these pixels are very similar to each other when we consider all the examples. And there are other parts here in the shape of the number and so on. So now we can take the original data, we can reduce these 64 features, 64 pixels to 16 and project it back on the original space. So this is basically this part here, doing the reverse transform. And what we're doing here is we're setting all the pixels in this cluster get the average value, and they just have that single value uniformly. The same for all the clusters. So you can see that this is the original data. This is the one with the simplified features, with 16 features. We can still see somehow the numbers there. It's not as clear, but we note that it's easy to see that this is a 0, 1. The 2 is a bit out of focus, but we can see it in some cases, 3, 4, and so on. But we can also represent this with the 16 features. So this would be the reduced version. They are no longer recognizable as numbers because now the pixels are out of order. I just took the 16 of them and put in a square of 4 by 4. But you can see that the 0 is different from the 1, and it's different from the 2, 3, and so on. So if we are trying to use this for a classification, for training a classifier, there's still in the features information to distinguish between the different things. So this is an example of using clustering to reduce the dimensionality of our data by aggregating features instead of aggregating examples. So to sum up this part, we saw this idea of hierarchical clustering as nesting clusters. We have clusters within clusters and producing a hierarchy there. And for that, we need not only to measure the affinity or dissimilarity between examples, but also to apply some measure of similarity or dissimilarity between clusters. And that one is called linkage. It's the criteria we use, or the measure we use, to determine whether clusters are further apart or more similar. Then we saw two ways of doing hierarchical clustering. Starting from the bottom, so everything is split apart, and we agglomerate, we bring them together and create a hierarchy. So this agglomerative clustering is an example of a clustering algorithm that does this, bottom up. Top down would be start with a single cluster and then split many times, as many as we want, or until we have the complete tree. So bisecting k-mean is one example of an algorithm to do divisive clustering. We also saw how we can apply clustering to features instead of examples in order to simplify the feature set. So you can you have this documentation on clustering on scikit-learn with lots of examples. The tutorial this week also will be about just seeing what the clustering algorithms do, and you have also this section on Alpine if you want to read more.